So good morning. Let's get started here. Mitadru, over to you.
So hello and welcome everyone. So is my screen visible?
Yes.
Okay. So let us just start. Okay. So good morning everyone. This is Mitadru Datta from CellStrat AI Lab and IIT Kharagpur. So this is our second webinar. In our last webinar, we have seen an overview of the Stable Diffusion, how it works, and we had also seen in detail of how the forward process works. And so today we are going to work with exactly how our unit architecture will work here, and basically the backward process also, and some other stuffs like positional encoding and all. So so before exactly going into the batch training, we should, I think we should take a quick recap of what we did last webinar, so as to get a better understanding and to relate stuffs quite easily. So we had seen the forward process being this denoising noising process of the initial image, which we had denoted by q, distribution q at t given t minus 1. So from 0 to t, we are just noising the image, and then at different timestamp, we are collecting noisy images and then subtracting the noise to get a new image with some features of the prompt. And the prompt would have multiple words. So the words inside the prompt would have multiple meanings, and all those meanings combined would give us the final image. So basically, so to give just a quick overview of what exactly happens. So we give a prompt. It has many words. So with each word there is an image associated with that, and that image is fed in the forward process. The forward process is just the noising of that image and until it becomes a Gaussian noise. Now every time we don't need to make the images completely Gaussian noisy, so we can just like, for typical value of capital T here would be t equals to 1000 times until we obtain a normal distribution of mean 0 and variance 1. But we collect images from different timestamps and then feed it into our unit architecture, which would basically detect how much noise and how much noise should be subtracted from the combined image. So that we will see today. So this was basically our forward process, and so yeah, let us just start with today's. So we had also seen of what this beta means. If this beta, this can be viewed as how much noise we want to be added in the next step with respect to t minus 1. So I'd explained the forward process, and I had also explained how we in one step we can calculate. We had this parameterization trick for normal random variable, and we can simply get to the final noisy image at any given timestamp t using this formula. And so we directly calculated the distribution at any timestamp t without just iterating over all of the images at each noise. So as I was telling you that not necessarily we have to take the complete noisy image. We can take noisy image from different timestamps from different cars, and we can just feed it into our model. Model would predict the noise, and we would subtract the noise, and then maybe the result would be some artistic car or some new type of car. So this was the overall overview of our last webinar. So in this webinar, we will in detail see the backward process as well as the training, as well as how this unit architecture works. So in some in even if in some of the latest extensions of Dream Booth, which I explored, I found that they are also using the unit architecture. So not just the traditional or old models. So even uh, latest versions of HD are also using the unit architecture, but like there are different phases of that. So they do it like they feed the attention modules and very complicated stuffs from OpenAI. That also we will give a high level explanation of and try to make a sense of how exactly it works and how we can tune the hyperparameters or how we can fine tune with our new models. So so the how the unit functions in batch training. So as you know that unit is a popular model for image segmentation. So output has the same shape as the input. So we do the downsampling and upsampling. I am assuming you all know this. And initial downsampling would also contain some convolutional layers. So it is a combined model of and downsampling, upsampling. And as you can see, the input and the output has the same shape. And there are some links which across time, I mean that at some time t, the image which is being processed here receive receives some other information from other image which is being fed at another timestamp t, so as to combine the features of those image also. So that is done by self and cross attention modules, which we will discuss. And so that's how exactly one image is getting the features of other images from the noisy samples, and then there we are just subtracting the noise in some of the layers, and we are getting a final artistic view of some maybe car or something. So this is just general discussion about some attention functions so as to give a better understanding. So transformer models apply an evolving set of mathematical techniques known as cross attention or self attention. So cross attention, as I told you, it is spread across different timestamps, and we will see what exactly self-attention would mean. So it detects in subtle ways that how some even distinct data elements in a series influence and depend on each other. So just to give a overview of and sense of how, just to make a sense of how exactly, what exactly it means, self-attention actually helps us to find meaning. So suppose we have a sentence, sheep poured water from the pitcher to the cup until it was full. So here it refers to the cup. But if the same sentence we just change the word full with empty, she poured water from the pitcher to the cup until it was empty, here it refers to the pitcher. So using the self-attention modules, the neural network while processing this word also takes also tries to just relate this word with other kinds of words and try to make a meaning of what, like this is similar to a human paying attention, right? So so that's how we call self attention. So there are many advanced self attention algorithms. There are I mean that there are some neural network architecture known as attention modules. So the architecture name is only attention, and like there has been even some books written like Attention is All You Need by some expert AI researchers from Facebook and OpenAI. So yeah, it is like a really complicated process, but this is the overview of how things work, how exactly it tries to keep a control over something which is also far away, affecting the current word or the current state of the image. So attention queries are typically executed in parallel by calculating a matrix of equation, what is known as multi-headed attention. So while analyzing one word, it is not necessary that I will have attention from only some particular words. I can have multiple attention from multiple other places too. So multi-headed attention combines both self-attention and cross-attention. So basically what is happening, our model will take a noisy image with, let's say, 3 color channels and predict the noise in the image. Assuming the variance to be set fixed, we just predict the noise in the image. We will output only one value per pixel, only one value of the noise per pixel. And the model basically learns the mean of the Gaussian distribution of the images. So as you know, a Gaussian curve, the mean of the Gaussian distribution of the pixels, the model tries to learn and tries to predict the noise in the image. It from the, as I told you, from the self and cross attention stuffs, it would also predict how much noise should we subtract, and also it would take information from previous timestamp images or maybe future timestamps of other images, and then it would get a value of the noise, the mean of the Gaussian distribution, and then it would subtract that to get a final image. So we will see of how this backward process is working. So let's just redefine our variables. So this x0 means in the forward process, we went from x0 to x of t. And now we are going from assuming that we have x of t, we are going to the final image. And in the process, like we are not just going directly, I will not just directly apply a formula and directly jump to the final image, because that's not how we want. Like if we give a single image, we don't want the same image to happen in the output, right? So as of now, I will assume that I'm directly jumping, but actually what is happening, I told you that we also have information from other timestamp of other images too, which is fed into this backward process, and then only the things happen. So here I am just assuming that I have a noisy image and I'm just denoising that. So once we get the noise, we can start out the parameterized backward process.
So just to recap, your forward process was to take the image and arrive at noise. And
yeah,
now you're training a model to go back from noise all the way back to original image, right?
yeah, yes. So once we get the noise, we can start out the parameterized backward process. So let's say we have a distribution of, let's say, the image X. The image is basically a 3D NumPy array or maybe tensor. So we have that. This is the probability distribution. Let's say it's the normal random variable. As I told you, this complete noise is actually what? This is an image with normal distribution whose mean is 0 and variance is 1. So that's how complete noise basically what is the definition of complete noise. Complete Gaussian noise, in fact. So as you will be knowing from your high school level that the normal distribution of 0, 1 means the Gaussian distribution. So we can just traverse from p of x, like we want to get p of x0, we want to get the distribution of the image 0. So we can just do like the distribution of the last image multiplied by distribution of, this is the complete noise, distribution of the complete noise multiplied by the distribution of. So this is basically a Markov process, as I told you, that from going from one timestamp to another, it's from just the previous timestamp. So what we need to have information is only about the previous state of the image. We don't need to have information about any other state. So this is the formula of the Markov process. So if you remember, a similar kind of formula I've also explained in my previous video in the forward, in the previous webinar in the forward process. So this is just the reverse of that, and the formula is same as that of a Markov process. So the density P is defined by the predicted Gaussian noise. So just we once we get a noise value from the neural network architecture, we just subtract that. So this is just an intuitive denoising formula. The denoising formula actually looks a lot complicated, but yeah, but actually it would because the neural networks has it is the noise is being predicted by the network, right? So it would be a lot complicated. We are just subtracting. We are assuming that we are getting just the noise. We will get the previous timestamp of the image. So like other generative frameworks, diffusion models can also be made to sample conditionally given some variable of interest like a class level. Just feed the conditioning variable as an input during training. So as I showed you in the previous webinar that
I mean, there was a basic question on chat actually.
Yeah.
So
Yes.
when to do backward process, when to do forward process. So folks, this is actually a second webinar there was a first one. So what is stable diffusion? Stable diffusion is a way of training a neural network and taking an image and generating noise. So the Y label is the noise. So then in the backward process, you go back from noise to image. So by doing so, you have now magically trained how to generate image from noise. So forward process is simply going from image to noise. Backward process is reverse training from noise to image. So the idea is to train an image generator from noise. So the backward process will achieve the magic of image generation from noise. So in the first webinar, Mitadru explained forward propagation. Now he's explaining the back training step. So with
Okay.
that summary, you can continue, Mitadru, actually.
Okay, sure. So yeah, like other generative frameworks, diffusion model can be made to sample conditionally on some given variables of interest, like a class level. So how is this exactly working? We'll try to get a feel. So last webinar, I gave a prompt to our code. The prompt was something like an astronaut riding a horse, and the output was also very appropriate. So with an astronaut, so this is an abstract image. So how is it exactly combining? We take some other classifier. Let's say the model knows how riding means. What does riding looks like? And the model also knows what a horse look like. The model also knows what an astronaut looks like. So it is just combining the information, right? So how exactly it is preserving the information? Means in the denoising process, why aren't we exactly losing the information? So diffusion models can be made to sample conditionally given some variable of interest. So we have few variable of interest like the horse, and so a basic classifier would try to predict, would actually very successfully predict how a horse looks like. So that we classifier, that basic classifier, we can combine with our unit architecture and made, and while noising, we can like make it sample conditionally given some variable of interest. So we are just denoising here. So while back process, we need to take care of all this, because we from noisy image we are going to the our artistic image or whatever. So we can't just subtract any noise, or we can't just do that. So we need some other classifier help which would give us information on which pixels or exactly which portions of the image to preserve, and like how a horse looks like, we should just preserve the semantic structure of the horse. So diffusion model can be made to sample conditionally given some variable of interest like a class level. So also to achieve a desired image, the diffusion process could be guided with a separate classifier, as I was telling you. So the one, we have a classifier which knows how an horse looks like. So that classifier would guide us during the denoising process on how to not lose the semantic information of the horse. So we can take a trained classifier and push the reverse diffusion process in the direction of the gradient of the target level probability with respect to the noise image. So from our basic neural network idea, we all know that during our back propagation algorithm is nothing means continuously having derivative of with chain rule, right? So so as we are going in the back propagation, the direction of gradient, we need to now also take care of in which direction our gradient would go, how we are going to maximize and minimize our loss function. So this classifier would also help in the reverse diffusion process in deciding the direction of the gradient of the target level probability. So the target level, let's say the horse or the astronaut, the probability with the current noise image. So here labels may be higher dimensional text images. So yeah, just so I mean to say that labels does not necessarily mean, of course, not necessarily mean just single word. So it may be higher dimensional text images. So if we are given a prompt, we will apply some basic NLP like stuff like the this tokenizer and stuff, which we will which will help us to means remove the useless words which are not useful for our neural network, and that then the remaining words we have as the labels, which may be of course a higher dimensional text or maybe images. So what exactly are we doing? This, let's say this, we have this as our data manifold. Now from where we are getting this data manifold? This data manifold, after tokenizing, after performing some basic NLP operations on our the text prompt, we get something known as data manifold. So wherever we go, we have to optimize our way such that all the information in the data manifold are used. So suppose we are giving 5 to 6 words which are useful in our text prompt, all the information should be preserved. We get the data manifold of like a range of values of pixels for which a horse would exactly look like a horse, and the car would look like a car, and astronaut would look like an astronaut and stuff. So this way we get a data manifold. We are at a random point now, let's say random noisy point, not exactly in the middle, but somewhere random. What we are doing is we are going away from the data manifold, the time when we have noisy image. So in the forward process, here we get a complete noisy image, and then we are again reversing back. What are we achieving exactly? You should question that what are we gaining by doing just back and forth? What exactly, how exactly it works? So we have to come at an optimal point in our data manifold. We can visualize in this way. So actually, if you see the Stable Diffusion research paper, it had a lot of complex mathematics. To get a overview with some like complex but not that difficult maths and integration, which is like which would be difficult to explain or difficult to understand. I am trying to explain in this data manifold way. So what are we doing exactly? We are just optimizing our path, and we are just trying to find a point in the data manifold. So find an optimized point basically. So now question comes that which path we should travel. We can travel from any path, right? Like once we go to the noisy image, and then we can travel back to our optimal point in many paths. And the question really arises here that is there a one optimal point? We have a lot of space in the data manifold. What if I come our optimal point, let's say we come to somewhere here or maybe some other place which also gives us some good results, right? So are we at all given means from which path should I follow to get our position with the minimum loss or with the maximum efficiency?
But
So
Mitadru, while coming back, we do need randomization, right? Because we don't want to
yes,
generate similar image every single time.
yes, that's also true. That's also true.
So we don't want
So
to arrive at the average of the image which has been learned. We want to
yeah,
arrive
yeah,
at
yeah.
somewhat newer, novel images.
So actually, what we would see that there is not only one point which we can arrive. We can arrive at multiple points. So running how we will see that exactly how that running the classifier different times we get different types of output. So why exactly that happens? So every time it lands up in different areas of the data manifold, and every times it may find also different paths, but it should not go to a really wrong path. So how to exactly maximize that lower bound? So we will see that just. So this is just the integration means what? Just the traveling. Uh, we are just we are finding the pathway of coming to our like the image, right? X of 0 means the distribution of the final output image. Like this from XT we are coming back, and just we just want to see that how we can just maximize our means chances of getting a nice image. So while returning back, what exactly we are maximizing? Question arises. what we are basically maximizing the likelihood objective of the given labels to be true. Yeah, that makes a lot of sense, right? We are basically maximizing the likelihood objective of the given labels to be true. And this likelihood objective, as we will see, is also a log likelihood function, which, like, you must be aware of something called Shannon entropy, which we used in some basic logistic regression functions like pi minus of pi log of pi. So that is what the log entropy function. So maximum likelihood objective, we will assume it to be a log function of the given labels to be true. So we have the labels. To make that true, we have some maximum likelihood objective. Those objective we are basically trying to maximize while coming back. So we have to now marginalize over all possible trajectory we could have arrived at x0 when starting from a noisy sample, right? So we have to just visualize all possible trajectories and find out which is the best. Or as I told you that we would not be able to come exact means predict at what point we are coming, but we will means we can construct an inequality, and that inequality would say that where you should not go. So those portion we would not go, and from where we would actually go to just get a correct outcome. So however, it turns out that we can only maximize the lower variational bound. So as I told you that our loss function is here is not a definite sum loss function which can be just written like in one equation. We have to just minimize that. This is not true here. So we cannot maximize any efficiency. We can only maximize a lower bound. So lower bound will that even that lower bound can vary. That's why we are maximizing that. So as I told you, let x be the observed variable and z be the latent variable. So just a recap, small recap from the previous webinar. We had the x as the observed variables, and using some factor analysis or PCA or maybe some other statistical methods, we are converting our observed variable to some latent variables. This is done in order for faster processing, maybe, and then like a lot of other reasons to make the model some ease for calculation. So our neural network architecture or our forward process, everything, even these variable x are actually these capital X variables, which I am pointing to right now. These are also latent variables. Means in our entire of backward process and the entire of forward process, we used only the latent variables for traverse. So we just convert them from observed to latent variables. So I also told you that that could be done with something known as variational encoder and stuff like this, which I explained, I think. And then we have the backward process. So basically I told you we will be taking a log probability, which would be greater than or equal to variational lower bound. So while coming back, we are trying to maximize this variational lower bound. So let us just first calculate what exactly is the lower bound. So log of px can be written as a joint distribution of integral probability. And this joint distribution can be visualized by multiplying some other distribution q of z, whose loss entropy would give like the Shannon entropy function. So this is just, we will see why exactly we are just multiplying qz and qz in the numerator and denominator. So we will at end see that the more our qz is closer to value of p of x given that, so we will see the closeness of this, and then like which signifies the degree of closeness of the two distribution qz. So we take a random distribution qz and just multiply that, and we have this eq is by hz, like we have this Shannon entropy function. So let this integral output be represented by some function e of q, which is basically this p of qz by qz. So the definition you can also write now. There is something known as Jensen's inequality. You can search that out in the internet. So this said that f of g of x, given some conditions, f of g of x should be greater than g of f of x. So we just flip that, and E of Q, we can just take this Q out, like log, we can write P log of P of X give X given Z. This is the joint distribution of the probability, which is not exactly same as the normal probability, as you would be knowing. So log of P Q of Z minus log of Q of Z, we can write that. And we can just take the E of Q of uh, log of P of Z with the Shannon entropy function. So this is basically our lower bound. So I told you, while coming back to our data manifold, what we can see that we have a lower bound. So at least from, like, while coming out, coming back, we should not means be lower than this bound. That's what we are trying to just say. So we also define something known as K divergence term. So this term was actually experimental, and like in the research paper, you will find the derivation of like how exactly the scale divergence term works. We use in many applications of machine learning nowadays scale divergence term, which signifies basically the degree of closeness of the two distribution P of Z given X and Q of Z. So as these two distribution get closer, the fraction would get close to 1, and we know that log of 1 is 0, so the entire term would go to 0. So this scale divergence term would says nothing but like the degree of closeness of two objects, of two distributions. So this is defined by this integral. And so yeah, so you might be wondering where is the differentiation of dz. So that's exactly here it is, because it is a joint distribution. So we write it this way. So the lower bound can also be expressed as something like this. So after solving this integral, I can give you the website link, like this source. Here the complete derivation is done from this integral to this result. And this lower bound can also be expressed as this. So this is just obtained by this. So what if you solve this integral now, you will get this L term plus this log of P of X term. So you can express it in this way. So this is obtained by solving the above integral. So what is important actually is that this scale divergence term is always greater than equal to 0. Why? Once again, so yeah, that's true, right? And once again, we get log of P of X greater than equals to L. So here what we have done, log of P of X is greater than equals to L. So the same equation we are getting. In fact, we get another additional information now, is that in fact this difference between them is exactly the KL divergence term and the approximation of the true distribution. So KL divergence term basically gives us an approximation of the two distribution. So there are other reconstruction. We are just trying to reconstruct the image, right? So there are other reconstructing images in signal processing. You might be knowing stuff like sync reconstruction filter. So those filter also we can apply. So those filter helps us to. So what if you would just take one single image, denoise it, and then like noise it, and then again denoise it, forward and just backward process if you do, then you would get not exactly the same image but something different. Like maybe it will be more noisy. We cannot get the exact information. So how we approximate that information using this scale divergence term. So the key takeaway from the math of the two slides was that after maximizing the lower bound, we could only take those values of log of px in the iteration which are above the variational lower bound. Hence, we get a range of possible output images. So this is basically the reason why running the model repeatedly, even with the same prompt, exactly same words, would give us different output every time. So what is the model seeing is that log of p of x should be greater than equals to L, and which should be something KL divergence term. It is getting a range of possibilities to land into the data method. So just that. So now we would discuss something known as step encoding. So this is something which is not not specific to Stable Diffusion, but it is very important for Stable Diffusion also. You might have seen this time step encoding stuff in some other transformer architectures maybe. So this neural network has shared parameters between time. I told you this. I told this fact previously also. So the model need to filter out noises from two pictures having different noise intensities. So, so two pictures which are at different timestamp would have different noise intensities. So model need to filter out two pictures, two different noise intensities, right? So to circumvent this, we use positional embeddings which were presented in the transformer model. So they are a clever way to encode the discrete positional information steps. So transformer use some smart positional encoding scheme. So here we would see something known as sine cos positional encoding scheme. So where each positional index is mapped to a vector. So each index is mapped to a vector. Hence the output of the positional encoding is a matrix. Where each row of the matrix represent an encoded object of the sequence summed with its positional information. So what exactly this means in some layman terms I can explain you is that this timestamp image sequence while feeding into our network, we are in our network we are feeding different timestamp images, right? We want to get some artistic car maybe. So we need to keep a track of what it is which index images is going inside the image, inside the unit architecture. So since there are a lot of timestamp, we can't just give indexes to that like we used in normal list indexing 0 1 2 3. We can't just do that. We have to give a range of probability. So this vector of positional encoding signify that we that at that position of timestamp we are having this image. So it would point out that image is being processed at this timestamp now. So it would just keep a track of the information. This timestamp encoding is doing that. So the transformer in general use positional encoders to tag data elements coming in and out of the network. Attention unit followed those tags, calculating a kind of algebraic map of how each element relates to other. So as I said, in general, we use positional encoders to tag data elements coming in and out of the network. We just keep it like we can't just feed images into our network and lose the track of everything, and then like that cannot happen, right? And as you will be knowing that we have to pass through the network again and again this to get the final image. So so to keep a track of data elements coming in and out of the network, we use this stem positional encoding. So this attention unit follows these tags, calculating a kind of algebraic map. So what kind of algebraic map? We are going to see that. The positional encoding is the scheme through which the knowledge of the order of the object is and in a sequence is also maintained. So if we are going to keep a track of that using those vector notations, we can also keep a knowledge of the object, the position in the sequence of how the objects is coming in and out. The knowledge of the order of the object in the sequence while fitting in and out of the neural network would be maintained. So how to do that? Suppose we have an input sequence of length L and require the position of the kth object within this sequence. Then the positional encoding would be given by sine and cosine functions of varying frequencies. So here k is the position of the object in the input image and d is the dimension of the embedding space. So we take this formula for granted. And why exactly we are taking this? So we will just see that what our objective was, this vector, to construct this vector, right? So with this vector, we will keep a track of this image. So we define first what each element of the vector will be in terms of sine and cosine function, and then we try to keep a track. So we define the elements in this way. So the p, k, comma j is the position function for mapping a position k to the index j, comma k, comma j of the positional matrix, and n is usually a user-defined scalar. So example 10,000. So in some so 10,000 value was actually taken in the research paper of this. So that's why I'm written this. So as I was telling, P00 we have the formula now in front of us. So P00, P01, all the values we can just calculate, index of our token, timestamp image sequence. So once we get all these values, we can just plot something known as positional encoding matrix. So this matrix is for n equals to 10,000 and d equals to 512, sequence length being 100. So we will follow this particular line. Let's say this, how to interpret this. Let's say this color we are taking up, and through this color, whichever region we get, those region we have similar timestamp vectors, but each vertical line would give us different timestamp. So this is basically continuous timestamp of data. So why exactly we could have just given 0, 1, 2, 3 to the data, but by using this map, the neural network architecture or the other attention modules can keep a better track of just by following the color and stuff like that. So it is just, this is a matrix with the continuous values of data, numerical values, and those numerical values which have a corresponding color in the pixel are just converted to that. So that's how basically timestamp positional encoding is done. So let us just see some of the extension, and so basically how far can you go with this stable diffusion. So we are basically done with the backward process also. And so even if you have not understood the overall mathematics, you just try to keep a track of what each equation means, and this would help us to like adjust the hyperparameters and stuff like that. Even if we don't know the exact equations of how those work, but like if we know that this timestamp encoding means this, so we can do a lot of things, lot of tuning with our model. So just let us just see how far can we go with stable diffusion. There is some, I think you must have seen this infinite zoom in some Instagram reels or something like that. So this can be created using stable diffusion. So the process is quite simple. Just generate an image using stable diffusion, scale the image down and copy paste it to the center, and then mask out a boundary outside the small copy. That mask we are not going to do much analysis using stable diffusion in painting. So this requires in painting also, which I am going to say in some other slide. So this stable diffusion in painting is then done to fill in the mask part. So we mask out some portion, and that portion and the other portions we are not just really caring about. And what in painting does is that it would just fill the masked portion. It would not change the other unmasked portion, but it would just relate the masked portion with the unmasked portion also. So that's how in painting works.
Why you have to mask it? You will be truncating the outside portion, no?
Yeah, so sir, first let's say we have an image, we are cropping it out, we are resizing it and putting it in the center. And then like it should look same as the other same as the boundary, right? Like
no, you will be cropping the
yeah,
center.
we will cropping, and then we will scale down the image to the center. But like if we feed it directly without masking, masking is just a way like to tell the stable diffusion that don't take the other pixels of the image into your consideration. Like if we just scale it down and then feed that image and the other image also, the stable, and just fit it into our stable diffusion architecture, it can predict anything, right? Like any image it can predict. So maybe some other thing, that image to image classifier basis. So what in painting does is that it tells the stable diffusion that now don't interact with other portions of the image. Just focus on this portion and do some operation on that. And then we again just resize that, and then again resize that, and then this way we will get basically. So I would like to go to the inpainting slide once. So suppose we are just replacing this apples with oranges. So we crop out this now, and if we feed these two images separately in our stable diffusion, then it will just combine everything and just create a final image. Like this leaf portion is exactly same as this portion, right? But still it is the feel is as if only the apples are replaced. So this we using the mask, we tell our model that don't interact with the boundary. While creating the oranges, don't just interact much with the boundary. Like don't alter them much. So I should have kept this inpainting slide, I think, first. So just using a similar manner, zoom in and zoom out we can do. So the size of the image is generated using the initial prompt is gradually decreased. This created a blank space between the image and the border and the resized image. The additional space is filled using the diffusion model conditioned on the same prompt. So we are using the same prompt again and again here. One thing we should take care. So we are using the same prompt with the new image containing the blank space and the initial image as well as the mask. So using this zoom in and zoom out techniques, so it has been found out that we can now create infinite zooming fractals using stable diffusion's machine learning models. So once I enter Scottish line satellite image. So even it is found out that research is going on in this way that in the can be used to infinitely zoom the Google map to like a greater accuracies or something like that. And then image inpainting, I told you that the image inpainting is an image restore technique to remove the unwanted objects in an image or replace them with some other object, texture design or something. To perform the image inpainting, the user first draws a mask around the object or the pixels that need to be altered. After creating the mask, the user can tell the models how it should alter the mask pixel. So I want my mask pixel to be altered from apples to oranges. So the unmasked portion, the model will take care that it is not tampering much. So yeah, even the unfinished drawing, it can also generate finished drawing. So it can complete an incomplete drawing. So this is taken from one of the LinkedIn posts. So AI can now read your mind. So this is not that difficult. So but what exactly is done? The brain's fMRI signals are taken. Then there's generated image based on people's brain activity. So using those brain activity, we try to get some prompts or we try to get some images of like how if a brain portion of the brain is showing this kind of activity, then what must the person be possibly thinking of, and just predict it in that way. And this is some high level research going on, and like these images were presented to people and using these generated from AI, like the help of these images were not taken during the generation of these images, and it was found out that they were almost same using the brain's fMRI signals. So some research is also going on in this way, uh, like we are not, I don't think we are quite far away from that. Like even a person, what did the person dream of, we can keep a track and make a video of the person's dream. So like, that is also possible maybe in future. And so they reconstruct the high resolution and high accurate images from brain activity by using popular stable diffusion image generation method. This will change everything.
So MRI is not noise. See, MRI is a kind of a signal, right? An
Yeah,
electromagnetic signal.
yeah,
So from that you are generating image, but not necessarily from noise here,
yeah.
right? So it
Okay,
is kind
okay,
of a
okay.
signal to image translator. So they are
Okay.
using SD for this thing as well, huh? Okay.
So yeah, this thing I have to see like how exactly it is being converted to the information. This fMRI signal, what exactly it gives that it is able to predict this image. That is a thing to explore. Now also in the fashion industry, like how a cloth is exactly fitting you, that could be. So this is new facet. So this is not just random pictures I've taken from the internet where a person wearing masks and clothes. So these images are actually AI generated, a new facet and AI generated fashion campaign. So you can just go to this website designboom.com. You will find that they're actually doing this stable diffusion thing. So we will see some portion of medical imaging. So until now, foundation models trained in natural images and language have not performed well. Foundation models means they are talking of maybe the other generative models like GANs and stuff. So trained in natural images and language have not performed well when giving domain-specific tasks. Professional fields such as medicine and finance have their own jargon terminology and rules, which are not accounted for general training datasets, right? But one advantage presented itself in the team study. Radiologists always prepare a detailed text report that describes their findings in each image and analyze. So by adding this training data to their stable diffusion model, the team hoped the model could learn to create synthetic medical imaging data when prompted with relevant medical keywords. So if during our fine tuning or if during our training, let's say, we could make the model learn some medical keywords, then it is shown that the model can like predict the something like this is the real CXR image and this is the synthetic samples. So the if we use a keyword here known as pleural effusions, if so we use this keyword, the photo of a lung with X-ray visible pleural effusion. So this medical imaging, I mean the SD is used to can be used to like generate deformations in the lungs, the all possible deformations, and this helps in better analysis of the patient, better analysis of the X-ray of the patient. So that has been proved, but like it is still an ongoing research. It is also said that like sometimes the wrong output is also done, but then it is believed that it would give us quite a nice accuracy. Let's see. So this is also a three-step process, as I told you. The variational encoder, which compresses the source image to the latent variables, basically the uncompressed generated image. So that is the latent variables. We have the text encoder, which turns the natural language prompts into vectors that the autoencoders can understand. So using in the text encoder, we can also use that positional encoding they are directly using because they are converting two vectors using that sine and cosine thing. Maybe different thing they are using. And then the unit architecture, which functions as the brain of the image generation process. So called diffusion in the latent space. So everything is done in the latent space, as I have told you. The researchers created the data set to study the image. So this source is also the same. The image source of all these slides, following slides is also the same. So they randomly selected 10 frontal radiographs from each of the two public data sets, and like they added 5 hand selected images of normal chest x-rays and 5 images featuring a clearly visible abnormality. In this case, fluid buildup between tissue called a pleural effusion. So model was actually able to learn how pleural effusion look like and how there can be many cases of pleural effusion, which like can it is able to visualize. These images were paired with a set of simple text prompts for testing various ways of fine-tuning the components. So these are very specific tasks. So like if we are using SD for this, so we have to fine-tune it a specific way with the process they are using. Like they are adding 5 hand-selected images of normal chest rays and 5 featuring a clearly visible abnormality. And finally, they pulled a sample of 1 million generated prompts from some model open dataset, and they just tried to do that model training and just the fine tuning also. Yeah, that's all. Applications are like endless in this field. So I last webinar I also showed you the code. So let us just go and try to make sense of what our code. So
So
do we
some of
have time?
these areas,
Yeah.
do they need custom training with Dream Booth? For example, the MRI to image, won't it
Huh.
need a custom training with Dream Booth? It cannot do it off the bat.
Yeah, I think because uh, yeah, I'm not quite sure, but I think the dream booth we should use because what it does, it takes a concept and it preserves the concept in all of our text prompts, right? So here images may be different, but the background overall concept is same. So that concept portion can be fixed with dream booth, I think so. So we would just go and try to explain. We don't have much time, but still we will see.
Increase
So
the font a bit.
just a second.
Yes, good now.
Now it's clearly visible. Yeah.
Yeah.
So just 1 minute break. So this I also explained that I divided this notebook into 3 parts. So it is first necessary to understand the overall working of the 3 parts. Then we will go into how each part is working. So is this part 1 is basically taking a pre-trained weights and as well as pre-trained pipeline. The entire pipeline of the SD, I have just taken it from the diffusers library and I've created this part 1 of the notebook. So in the part 2, what I am doing is that I am just taking pre-trained and the variational encoders and stuff like that. They are also, those are also pre-trained weights and maybe pre-trained portions, but pipeline is not pre-trained. It's pipeline. So the pipeline, this diffusers library, they also taking some scheduler and clip text models. This clip text model is like from OpenAI. They're using that. But in part 3, what we would do is that from complete scratch, we would try to see. Neither complete scratch, I'm just writing. Neither pre-trained, it would be. Either the weights would also not be. And then, like we will see that in this, we, even after writing a lot of code and just we are not able to get that much of good results because I will try to explain why what exactly happening in our scratch model which we are not exactly trying which we are not able to do that what in the pre-trained in the pre-trained stuffs what exactly like OpenAI they are doing that we from this completely scratch thing we are not able to do. So I have some references for my help. So yeah. So first we will see the first part of the notebook. So we just first install the libraries. From diffusers, we install the entire pipeline. The entire pipeline I am using. I'm doing just nothing. I'm just loading the pipeline from the library. And the stable diffusion pipeline from pre-trained cause G-type. We just load the pipeline. And so I was just like, we are having I was just looking for that client project working, that HP thing, where like we had to create worksheets for kids. So for coloring portion, I was just trying to see whether uncolored portion this is able to predict or not. The uncolored unshaded drawing of a big flower. So I was just seeing that. So you can whatever the prompt is, you can just see that like uh, it can generate this from this pipeline variable which we loaded. Right. So this is quite simple. We can create an image grid. We can just create an image grid and according to our convenience can produce the number of images as we like. So num image is 3, so we can produce using some matplotlib, like I think subplot and stuff. So yeah, in the part 1 we just use the pipeline built from like pre-built pipeline and pre-trained weights. So here we will use the pre-trained weights, but we will load the different portions of the pipeline from the library, and then we will combine those portions. We will see how the pipeline is working. So we import torch and change to GPU mode. Yeah, we just change to DPU mode if it is available. And transformers, we import something known as clip text model and clip tokenizer, and diffusers we just autoencoder, the unit conditional model, and this scheduler which contains the timestamp stuffs also. So we just load the I had explained you the variational encoder. We convert this, we use this for converting the observed variables into the latent variables. So load the or load autoencoder module which will be used to decode the latency into this samples image space. Load the tokenizer and the text encoder. I also told you that the basic NLP operations, you can write simple code from that from the NLTK library also, but we are using tokenizer and encoder also, like we are just simply using this from pre-trained stuff. So this is like an OpenAI thing, clip tokenizer. And the unit model for generating the images, the unit 2D conditional model from pre-trained, we also load that. We load the separate portions differently. Okay, and from diffusers, we import LMS discrete scheduler. So this scheduler from pre-trained, so it loads the version. So what this scheduler and embeddings does, I would explain that. And we just convert our variational encoder, text encoder, and unit models to the torch device. I mean, the torch device was the GPU. And let's say we are trying to interpret this prompt. Let's say glass spaceship landing on water. So we set the height and width of the image, now inference steps, guidance scale, generator. So we are giving a torch that manual seed. So you will see that every in the code also gives the same output here because we are fixing this manual seed. So this is somehow altering the, means keeping the parameters fixed every time. If we just delete these statements every time the other images will be produced. This input we just take a we just tokenize that, perform basic NLP operations. So I have written something about torch.nograd. I think you know this already, but we will be using it again and again in code. So torch.nograd deactivate the autograd engine. So what is this? It eventually will reduce the memory usage and speed up computation. So to perform inference without gradient calculations, we aren't actually now updating our weights and maximizing some, minimizing some loss functions, and just we are not just changing our gradients to the value, right? We are just finding the text embeddings to make sure that there is no leaky text data in the model. So we know we don't need any gradient calculations for that. So we say that torch.nograd. So it will also help in like reducing the memory usage and speeding up the computation. So with torch.nograd, we define some text embeddings. As I also told you about the positional embeddings, we have the text embeddings which encodes. So we have the encoder portion here. And this text embedding, so let's say we give a prompt using some tokenizer, we get the tokens. This may be in some latent space. And using our clip model, this clip model is from OpenAI. So they are doing something, they are getting the text embeddings, which like in we will see that from our scratch, these things we are not able to do. Like in the OpenAI, they have done this clip model, which makes the execution quite faster, and like that we will see that 1 to 2 epochs in our final code will take a lot of time, like 12 minutes or something. So like it is like quite difficult to show you the all the epochs if we build from scratch, but here it is quite easy to show the final image also. So this text embedding, they are just loading from the text encoder from that clip library from OpenAI. And so these unconditional embeddings and those text embeddings increase the reconstruction ability. So if you search something like unconditional encode embeddings in Google, you will get like embedding as a random variable, taking values in reproducing kernel Hilbert space. So a lot of complicated stuff you will get. So the overall thing is that these embeddings, conditional embeddings, which we are loading, increase the reconstruction ability. So what is the reconstruction ability? So we also see that in the backward process there is some reconstruction, and you in some if you use some filters, sync reconstruction filters and stuff like that, these embeddings in some way they help to increase the reconstruction ability. So this is the reason 2.0 why we are like not being able to create such a good classifier in our part 3. So in our part 2, good SD model basically. So in our part 2 we will get a glass spacing landing on water. It's a fine image, I think. But so these small things is making a lot of difference in our output image. So these text embeddings, we just take that and we convert those into latent variables, and we also take the latent variables into our GPU, and we set the scheduler. This scheduler I had also told you, set the timestamps, num inference steps. So basically this time step encoding is also happening here. As I told you, what is going into the model, I'm just doing that. It is also just keeping a track. This latent, just we are just then all the operations are happening on the latent variables, right? And whatever time step encoding, we just need to apply those on the latent variables. Now that we are just expanding the littles if we are doing the classifier free gradient. So I told you something about classifier guidance, right? We I told you about something classifier guidance. That guidance not here basically. So classify free guidance to avoid the forward passes. So this is a latent model input. So so we are taking our unit architecture and predicting the noise. As I also told you that our unit architecture would basically predict the noise. From the image, we are getting the noise. So we just apply that and perform guidance also. So we have some guidance. This is classifier free guidance. So we need to check it out how exactly it happens. I told you how classifier guidance happens. In this slide, I told you that we can, to achieve a desired image, the decision product could be guided by a separate classifier. So classifier guidance, I told you. So they are doing some classifier free guidance here from using the noise predictions. And we just compute the noisy sample from xt to xt minus 1. So from the scheduler, we are just going one step. This and the decoding, this is entirely the decoding parameter. One by this is the decoding parameter. Like this, you can also calculate. But the model is, the unit architecture is built in this way that every time the image will be encoded in the same way and decoded in the same way, and like uh, the inside noise prediction and attention modules will take care that every time the same things are happening, but this decoding parameter is same every time. So this parameter is basically the decoding parameters which decodes our latent variables to something we can observe. So we can just also, we are then using this variational encoder. This I had also told you, this variational encoder has some other neural network inside that. So decoder, this is decoder. So if we just plot that image, we'll get our output of the prompt which we had taken initially. This prompt, glass spacing landing on water. So if from complete scratch, if we would try to create that, so here only the basic things we are doing. So if we can simulate the forward process, I think nicely, we can just write a function which would show the images by adding subplots. So, I'm using a Stanford cars dataset from Torch Vision, dataset.stanford cars. So, which has 8,000 training and 8,000 testing images. And this linear beta schedule, this is a function I'm using Torch linspace for that. This interpolates between the start for as many timestamps. So this is basically a series of noise adder, right? In the forward process, as I had told you, I had some formula, right? Forward process. We had this formula. So this signifies the amount of noise, this root over of 1 minus of beta t. This is our lead. This can be viewed as how much noise we want to add in the next step with respect to xt minus 1. So that how much noise we are trying to add, something will be within. We don't want to add noise really fast. So this interpolates between the start and end for as many time steps. And this is basically series noise adder. So we will get index from list. This is just a helper function. This returns a specific index t of the past lists of values. While considering the batch dimension, we will also take care of the batch dimension while getting index from a list. So we'll see how each of this function is working exactly. So here we now apply those formulas. Forward diffusion sample. So takes an image and the timestamp as input and returns a noisy version of that. So before applying this, you might be thinking that where this square root, these variables are coming from. So before running this function, we are defining some variables, recalculate different terms. So I told you stuffs like alpha was 1 minus beta. From that, exactly the same thing. Alpha was 1 minus beta. See, you can see that. And alpha comport means alpha dash. So we are just multiplying using comport variable. So alpha dash I had also defined in the, I am assuming that you can recall this. This alpha dash means alpha 0 into alpha 1, alpha 2 dash means alpha 0 into alpha 1 into alpha 2. So we are just applying all the math here. And we are taking up the square root and applying that formula. And alpha crumb t, we are getting index from list because at time t, we have to get the index from that list using that encoding or whatever I told you. So get index from the list. I think does that. And at time t, we found out this values. Okay.
It's a really complex program, Mitadru. You're not training
Yes.
the model here per se, right?
Yeah, I am also training it in the later portion. Like here, I've tried to do it totally from scratch. So
So are you saying you built SD pipeline from scratch?
actually, I've taken the help of an YouTube video whose link also
So
put
you are
in.
not using pre-trained SD model
No,
here.
no. Here I'm not using pretrained, and the result was that also not that great, but it would be great if we had run it from a lot of epochs. So
No,
this is
because
epochs.
SD is trained on massive cloud clusters.
Yeah.
So here you're training on a local collab. So
Yeah,
obviously you will not be able to beat SD performance, right?
yeah. Like
But
it
you
took
are
12
trying to
minutes to run
simulate.
for 3
You are
epochs.
simulating the entire behavior with your own code, huh?
Huh. Like that's
Okay.
what I was trying to do. And so I would just tell you a thing that so this is another algorithm for the we also do something upsampling and downsampling. So this algorithm I have just directly used this formula. So that was also in the code. So as you can see, as we increase the epochs here, at 100 epochs, we get something of a car, and like in 500 epochs also we will get close to that. So that's not possible to run on Colab. So yeah, so should I like continue with the explanation, or is it
I think you can just
fine?
do on a high level. Code is very granular. It's hard to
Yeah,
understand unless we all run it ourselves, right?
yeah. This code it runs properly in Colab.
No, but with your limited
Ah,
cloud capacity here, Were you able to get at least decent image generation?
No, like this, the output of this we can get this much only.
Because your image
Not,
generation would be very suboptimal compared to actual
yeah, yeah,
SD model, right? Because actual SD model is trained on
yes,
massive cloud clusters.
yeah. Then they do a lot of things like I told here that
Yeah, their program would be
uh,
significantly more complex, I am
they,
imagining, right?
this clip module and this they define these embeddings. This increase the reconstruction ability and a lot of things they do. Like I use the libraries there, but here I am not able to
I
do
mean, if
this.
you can crack an SD kind of model from scratch, you could literally launch a competitive startup,
Yeah, that's
correct? If you can train that kind of model from scratch, you could create a
yes,
competitor product, right?
yeah, that's true.
But good audacious attempt, I would say.
Yeah,
On a high level, you can explain. Line by line is not needed, it's quite granular code.
yeah. So I will just share the code also. So in the so overall in this portion, I am just applying all the math, whatever I've done in for the forward process, and we are just loading the transform data set. So here I am doing the data augmentation. So this thing we do in every touch like thing like we use the compose, but here I'm just defining a variable data transform. It would just do the data augmentation. That is the scaling, horizontal flipping, and stuff like that. And then we transform our data using the same compose thing, and then the train data and the test data which we loaded from torch vision, that both train and we apply the transform to those. So we are not testing anything right here. So I have the train and the test, both things I've used as training purpose. So definition is like show tensor image. So it converts the this portion is for converting the tensor to the PIL image, the reverse transformation of just the previous. So and then we are loading the data into a data loader, and then just we are just simulating of the forward process. So forward diffusion sample, whatever function we had written by applying those formulas. So I had also told how to jump from one timestamp directly to the other. That formula also we can use, but here the formula which I have used is that parameterization trick. There was some parameterization trick which I explained the forward process. So any normal distribution we can apply that this trick, this mean into this variation. This formula I'm using directly. We can also calculate just to simulate in a step-by-step manner. I use that formula. So then this is the standard unit architecture. You can get this on the internet easily. This sinusoidal positional embeddings in that transformer module. I had also written this like exponential and then sine and cos embeddings. Simple unit module. We are just creating this modules, the hidden layers and all. Now this also convert has upsampling and downsampling techniques, which are applied using this algorithm. So that this is also taken from that research paper. This algorithm of sampling and downsampling, we apply that. And convolution, we also use some convolutional layer, as you can see, conv2D and conv2D I've used. So yeah, so this is our how our unit architecture basically looks. And to get the loss, we are just using something like this. This is our loss. We are just doing a L2 norm of the loss from the predicted noise. So this is a simple loss function. Actually, this is also not the actual loss function which is used. The loss function also I simplify things. We have to just do this. So we call the model to predict the noise in the image, and then the denoised image here. So that this also we fixed proj.nograd, and this sample timestamp, this applies noise to the image, and if we are not in the last step yet, so we just do the apply sample noise. So it just creates a sample noise and then applies that, as we have seen, and then the denoising stuff they are doing here. So the denoising, whatever variables whatever functions I have defined here, this sinusoidal positional embeddings, these functions are being called here, and this is the usual four step that PyTorch thing. Training is like quite simple. Like we set optimizer to 0, then let's just select that I'm optimizer, and then we just go for and get the loss. And as we do loss dot backward and optimizer the dot step. So this basically gets the loss and feeds into the backward propagation algorithm. And this optimizer the step, using that Adam optimizer, it updates the weights. These are basic things only. So this is that 4-step general process of training a neural network. And so yeah, that's how epoch 1, 0, 1, 2 will look like. And like someone over the web has also done in some.
No, can you show the image generated by your model?
So like in 500 epochs, the images will be something like this. This output.
Which one? The second row?
You can say this 500 epochs. This portion of it.
The first row? Okay.
Like,
so what does the 3 rows imply here?
So every time, like, this is going from one epoch to another. Like, this is epoch 1. So this is every time we have to iteratively feed into the model.
Right.
So,
Got it.
Denoise, and then again.
So this is forward path. So the reverse path.
This is the forward path, and simultaneously this y-axis downside will be the reverse path.
Okay.
This.
So you're getting some images.
Like since everything is from scratch here, so not much I can do.
Yes.
So yeah, then like. So that's all from this webinar, I think. I had also some control net stuffs ready. So if we had time, I could have explained that. But like we are already have 1.5 hours of webinar. So sir, should we like call it a day then?
You are done anyways, right?
Yeah.
Or more is left?
No, the basic like I kept this control net extension ready. So that
you have control net also? Okay.
Yeah, but like I kept this if time remains, like in the last webinar 1 hour it was. So I thought that
We have studied the control net mechanism which has come out from Stanford, huh?
So not exactly that mechanism, but how exactly we are.
One of our guys is supposed to present control net in May. So, but it's good. So I think we also need Dream Booth. How to custom train with Dream Booth, Mitadru.
Okay, I will try to find out that. But as of now, like some research on Dream Booth I've done.
That's okay. Not today, of course, but in a different webinar, we can plan.
But I had some, but like this requires some 16 GB RAM or something like that. I have to see that. Like there are other fast Dream Boot and stuff like that.
Yeah, on CellStrat Hub in the Gamma tier, I think we have 16 GB RAM, right? Or we don't?
Okay, yes.
Yeah, in CellStrat Hub, you can get the Gamma tier.
Yeah, that I'm having. So. Yeah, 16 GB NVIDIA.
Correct.
So we'll try it out here also.
Yeah. Okay, good session. Any other questions, audience? So it's fairly deeply technical and mathematical. So it needs some time to for all of us to sort of grasp our head around it. It is quite complex indeed. But basically, it is the same neural network concept we have been studying for years with the Gaussian distribution and probability, maximum likelihood estimation. So it's not really rocket science compared to what we have done last 5 years. It's just a way of setting it up and getting the techniques we have been studying for years to do a certain objective.
Yeah, so there were some questions like, would it be possible to build a 3D model? So 3D model is also built, like I put it in one of my slides. So like some of the research is being done. Like if you give the prompt like a person walking and picking up an apple, so will like show the 3D person actually walking and picking up an apple. So that level is also trying to make fMRI work by labeling first to train the model. So that is a thing to check out. That's how exactly fMRI that. So I think using this something we can do some training, like if fMRI model is generating these signals, then the person is thinking about this object. In this way, we can just like fine tune or train our model. We can give examples of many fMRI signals. Maybe I'm just guessing that I'm yet to discover this.
Okay, great. Any other thoughts, audience? Okay, so great session, Mitadru. We'll look to your next sessions on Dream Booth and other things. So
Yes.
very detailed and mathematical. So nice job. So I think we have some customer projects lined up. So we'll together tackle those.
Okay. Sure, sir.
Thank you all for joining. So we'll see you in the next weekend webinars. Have a good day, folks. Thanks, Mitadru.
Thanks a lot. Thanks a lot.